And then usually the other two are like, if you took pre-cal, like graph and sine and cosine, inverse trig questions, law of sines, law of cosines, stuff like that.
I think I have one inverse trig. One inverse trig and one like normal trig. I don't think I have four.
Huh?
I don't think I have four. I've done an inverse trig and a normal trig.
I mean, I don't know.
Oh.
Just traditionally, they've always said 4 trig questions, but they're also very secretive about what they put on there, so.
How's your weekend?
Good, how was yours? What? I thought there was something to that.
Is there something I'm missing? Because you made your library all week.
Well, I didn't think you were getting the homework done, but I just saw that you just finished.
Sorry.
I mean, you waited till the last second, so.
Yeah, you know, I'm resourceful with my time, is what
I
I'm
helped
saying.
you, I helped you.
Thank you, Sam.
But I didn't help that much.
We both got it wrong.
All right, good morning. If you guys would number your notes as 53 and the circuit is 54.
We'll get started here in just a second. Okay, Luna, I took you out, so you'll need to re-sign
Up for your punt time.
Thank you.
Okay, so last week we started doing first derivative test and using the first derivative, and we need to continue on to second derivative test. So I think most, if not everybody, got the notes turned in. But if you did not turn in number 51 in the Google Classroom,
That was the notes over extreme value theorem and mean value theorem. This would be your last opportunity to still get full credit. So if that applies to you, please come and give it to me real quick. Jonathan. Ben.
okay. All right, let's start off with 53, our notes on the second derivative test. So, like the second derivative, or like the first derivative test, we often use the first derivative. It has some helpful properties to it. Like if you want to know where it's increasing, decreasing,
You're going to be using the first derivative, but the first derivative test is really about finding relative maxes and mins. So second derivative test is pretty similar. The second derivative is going to tell us different information about the function, but the second derivative test has actually the same purpose as the first derivative test, finding relative maxes and relative mins. So before we get to that, we'll talk about why we, or
the characteristic of second derivative test we need to use, and that is something called concavity. So concavity is whether the function is concave up or concave down. So the parts that you will have to have memorized is when the second derivative is positive, your function will be concave up, because second derivative is like the derivative of the first derivative. So it's the rate of change of the rate of change. So you can see these little, I don't know how well they show up on yours, but there's a few little tangent lines in here. Each one of these tangent lines represents the rate of change. So the rate of change was negative, 0, positive. If the rate of change of the rate of change, the second derivative, is positive, it forces your function to be concave up. For the exact same reason, if the rate of change of the rate of change, the second derivative, is negative, so if that rate of change decreases over time, then you end up where your function is concave down. So first derivative tells us if a function is increasing, decreasing. Second derivative tells us if it's concave up or concave down. Okay, then there's something called inflection points, and inflection points are very similar to critical numbers with a few very important differences. Critical numbers are numbers that make the first derivative 0 or undefined. Critical numbers usually show up as relative maxes and relative mins. Inflection points can occur when the second derivative is 0 or undefined. But just because the second derivative is 0 or undefined, that's not enough to make it an inflection point, or a point of inflection. The other thing is that the concavity has to change. It's got to go from concave up to concave down, or concave down to concave up. It's got to change concavity at that point. The other part that's easily overlooked is when we say inflection point. If it's not a point on the graph, it can't be an inflection point. So a point on the graph where concavity changes is called inflection point. We'll find them by figuring out when the second derivative is 0 or undefined. So again, the reason why that's similar to critical numbers are when the first derivative is 0 or undefined. And whether those end up being relative maxes or mins, they're still critical numbers. Inflection points come from when the second derivative is 0 or undefined, but it takes more than just that to happen to be an inflection point. Okay, so let's look at a couple of examples here, and I'm going to ignore all the stuff we're supposed to get out of this, but let's say you were asked to either find the concavity of this function, when it's concave up, concave down, and or you were asked to find inflection points. You would need to know that both of those things deal with the second derivative. So you'd have to take the derivative of the derivative, and you're going to have to solve that for where it's 0 or undefined. Now, if you want to know where it's concave up or concave down, you're actually going to do one of these sign charts again, just like we did with the first derivative test. But x equals 0 makes the second derivative 0. So you need to put that this is maybe or possibly an inflection point. That word maybe is really important because it's not an inflection point yet. If you just make that shortcut and say, well, it's probably an inflection point, that's going to mess you up at some point. To be an inflection point, I need to know if the concavity is changing. So, in possible inflection points, these are the only places the concavity might be changing. So, if I want to know the concavity to the right of this, I would plug in a number into the second derivative. I would get positive 6. I could care less about the positive or about the 6, but I care that it's positive. because when the second derivative is positive, it's concave up. And then I could test a number to the left of 0, like maybe -1. Plug that into the second derivative. That would give me -6. And when the second derivative is negative, we know it's concave down. So we just make these little like miniature figures here. So it's a quick little summary. It's concave down till 0, and then it's concave up. So is x equals 0 a point on the function? And how do we know?
You need to change from downwards upwards.
One more time.
Is it like change from concave down to concave up?
No, I just want to know, is this a point on the graph?
Yes, because it doesn't make it undefined.
Doesn't make, what is it?
F second, or f of x.
There you go, f of x. We can plug in f of 0 exists. I don't care what it is, but it is a point on the graph. If you need a point, you're referring to the function. So, is it a point? Yes. Is it an inflection point? Well, it has to be a point on the graph, and the concavity has to be changing. So is the concavity changing at 0? Okay, so now that both of those things have been checked, now you can safely call it an inflection point, or cross off the word maybe. But don't assume it's an inflection point until you see the concavity changing. So this is one that we really know what the graph looks like, or you should know what it looks like. So let's just compare what the graph looks like to what we just did. This sign chart was just a quick way for me to visualize it as concave down till 0. So notice it opens downward till x equals 0, and then concave upwards after x equals 0. So if you want to know if it's increasing, decreasing, you still need first derivative. You want to know where it's concave up, concave down, that's second derivative. If the concavity is changing at a point on the function, we call it an inflection point. Inflection points can occur when the second derivative is 0 or undefined. Okay, now let's look at another example. So again, I'm going to ignore all of this, but that's what our takeaway needs to be. So let's find out if there's an inflection point for f is the cube root of x. So I know inflection points might occur at when the second derivative is 0 or undefined. So of course some derivatives are a little bit more work, but and you might want to simplify it a little bit if you think that helps. But this is an application of derivatives, specifically second derivative, so you're going to need second derivative. And if it wanted to know when the function is concave up or concave down or both, or find inflection points, we need to think about the concavity. And just like with critical numbers and relative maxes and mins, we don't want to check every x value. We just want to check the x values where it might be switching. So that's why we want to know when the second derivative equals 0, it doesn't, and when it's undefined, which would be at x equals 0. When the second derivative is 0 or undefined, you might, I'll put maybe, have an inflection point. That's different than critical numbers. Critical numbers are critical numbers if the first derivative is 0 or undefined, regardless of what else happens. Inflection points are only inflection points if it makes the second derivative 0 or undefined and makes the concavity change. So this is the only place that the concavity might be changing. So to know the concavity to the right of this, we can plug in a number into the second derivative. And again, sometimes the computation's a little hard, but all we really care is if it's positive or negative. If I plug 1 into the second derivative, I get a negative over a positive, which would be negative. When the second derivative is negative, it's concave down. And to know the concavity over here, plug in a number less than 0 into the second derivative. We would get a negative over a negative, which would be positive, which is concave up. Now, when you guys do your line charts, again, I try to model it the way that you guys need to, but if you're not writing some of this, like whether it's positive or negative, that could potentially hurt you on justification points on FRQs. This is concave up because I'm plugging this number into the second derivative and it was positive. That is a good justification. Without this, I don't know why you think this is concave up. Without this, I don't know what you plug the negative one into. Like, I mean, I hope it's the second derivative, but I can't assume that. Okay, so is x equals 0 a point on the function? Can we plug 0 into the original function? Okay, so that means it's a point. Is it an inflection point? Okay, why are you saying yes?
Because the concavity changes.
Right, it's a point on the function and the concavity changes. So now we just confirmed that x equals 0 is an inflection point. Okay, so the difference between example 1 and example 2 is example 1, we found an inflection point when the second derivative equals 0. Example 2, we found an inflection point when the second derivative is undefined. Most of the time it's when it equals 0, but you also have to check when it's undefined. You have to make that part of your thought process. Okay, and then finally one more example here. We will work with, again, I'm going to ignore all of this. This is what we should discover. But x to the fourth, if we wanted to know if it has any inflection points, those would occur when the second derivative is 0 or undefined. That appears to be 0. When you do your line chart, you should say x equals 0. Do not call it an inflection point. You don't know if it's an inflection point. It might be, it might not be. So I think it's a good idea to put maybe inflection point, and then we can come back and cross the word maybe out when we're sure. But the idea is, if this is possibly an inflection point, then the concavity might be changing here. This is the only place the concavity might be changing. So if I try x equals 1, whatever the concavity is here, that's going to be the concavity for 0 to infinity. So plugging in 1 into the second derivative gives me something positive, and when the second derivative is positive, our function is what? Okay, up. So we just draw a little picture of that, quick little visual. Trying something to the left of this inflection point, or possible inflection point, like -1, you still get something positive, so it's still concave up. So x equals 0 is a point on the function, because x equals 0 exists in the function, but the concavity did not change, so x equals 0 is not an inflection point. The concavity has to change. So just because there's numbers that make the second derivative 0 or undefined, you cannot assume that's an inflection point. You still have to test the concavity and you have to see that it changes. And if you don't know what x to the fourth looks like, it's just like a skinny version of x squared. It's a little steeper.
I have a question.
Yes.
So it's just the two conditions that it needs to meet?
To be an inflection point, yes.
Okay.
It's got to be a point, and concavity has to change. Okay, and if here's what x to the fourth looks like, notice how this matches up with our calculus. It's concave up till 0. Then at 0, the slope is 0. Then it's concave up again. Concave up, x equals 0, concave up. Okay. Now, all that being said, all of that is some good useful stuff to use the second derivative for. But that is not the second derivative test. Just like the first derivative helps us figure out increasing, decreasing, but the first derivative test is about finding local maxes and local mins. The second derivative test does the same thing that the first derivative test does. It's a different way to find local max and local mins. So the first part of this says, if the derivative is 0, like right here, I'm going to call this x equals c. If the derivative is 0 at x equals c, and the second derivative is positive, what does this mean? Concave up. So if it's concave up and the first derivative is 0, do you see how this point has to be at the bottom of your curve? Which means that it is a local min. Whereas if the first derivative is 0, so the slope there is 0, but it's concave down, do you see how that point is now at the top, which makes it a local max? That's what the second derivative test does. Helps you find local maxes and local mins. So we're going to be testing critical numbers where the first derivative is 0 or undefined, and then we're going to think about concavity. If it's a critical number and it's opening up, that critical number is a min. If it's a critical number and it's opening down, concave down, then that critical number is a max. And if you just think about whether it's opening up or down, you can see it, whether it's at the top or at the bottom. So you don't really need to memorize anything there. Now, I don't know, maybe this is just my opinion, but I think a lot of you guys will agree with me that if they do the same thing, the first derivative test and second derivative test do the same thing, why don't we just always use one of them? Well, truthfully, the second derivative test can fail, so if you only know one method, it needs to be the first derivative test. But that being said, the AP exam does phrase questions in a way that will test to see if you know the second derivative test, and where you can't use the first derivative test. So I will refer to that in just a second. Okay, so let's do this, and we're going to use the second derivative test here. So if the question was find any local maxes or mins of this function, the second derivative test still needs to know what are the critical numbers. Critical numbers still mean the same thing. When the first derivative is 0 or undefined. You can still do a line chart if you want to. Now, here's the difference between the first derivative test and the second derivative test. The first derivative test, you would plug in a number into the first derivative to see that this goes from decreasing to increasing, and then you would know this is a local min. Correct? The second derivative test says, wait, just plug in that critical number into the second derivative. Okay, so that means I got to take the second derivative. If I try to plug 0 into this, there's no x's, so there's nothing to plug in. So the second derivative is always positive, and when the second derivative is positive, it's concave up. And so if that's a critical number and it's concave up, then that critical number, you can see it's at the bottom. That critical number is a local min. Same result you would get from the first derivative test, but this could be easier, and sometimes this is necessary. Okay, so let's look at another one. I think we got 2 more examples here. Okay, if we were asked to find the local maxes and local mins of this, whether you're doing first derivative test or second derivative test, you're going to have to find the critical numbers. Both of them need the critical numbers. Of course, sometimes the derivative is harder and sometimes the algebra is harder, but I'm trying to focus on just focus on the calculus part on our notes here. X equals 0 is a critical number. That's all it takes to be a critical number. There's not more conditions like inflection points. Now, if you wanted to do the first derivative test, and you don't have to write this down, but you would plug in a number like -1 into the first derivative to see that it's decreasing, plug in a number like +1 to see that it's increasing, and then you're going to see that this must be a local min. To go from decreasing to increasing, it's local min. If you try to do the second derivative test, you still need to know the critical number, but instead of testing around the critical number like the first derivative test, you actually test the critical number himself. And of course, for second derivative test, you need to know the second derivative. If I plug 0 into the second derivative, what do I get? One more time. 0. Okay, so if the second derivative is 0, is it concave up or concave down? We don't know. This is where the second derivative test can fail sometimes. You need the second derivative test to be positive to know it's concave up and a relative min, or negative to know it's concave down and a relative max. But sometimes the second derivative test fails and you have to use the first derivative test. You need to know if it's concave up or concave down to know if it's a high point or a low point. So in this example, you would have to use first derivative test. Yes?
So if the first derivative test doesn't work and the second one does, or
First derivative test will always work.
and if it doesn't, it just means it doesn't.
No, first derivative test always works. Second derivative test doesn't always work.
Okay, gotcha.
So again, I said I would bring this up. If the first derivative test always works and the second derivative test sometimes doesn't work, why don't we just stick to the first derivative test? Well, again, they're going to, on the AP exam, they're going to test you on the second derivative test, and the way they're going to force you to use to say, well, I'll show you how they're going to force you to use it. Let's look at the last example. Here's one more. Okay, find the local extreme points of this function. So I'm going to try the second derivative test since that's what's new. For second derivative test, you still need to know the critical numbers. And again, this question doesn't say how to do it, so you could do whatever you wanted to. But if you think this function has one critical number as a multiple choice question, you're probably going to be confused because there's probably going to be, I don't know, this is not correct. What did I not consider here? Plus or minus. You take the square root of both sides. If you don't remember plus or minus, then you just lost a critical number and you just made the question a lot more complicated than it needs to be. Once again, just for comparing and contrasting sake, if this was the first derivative test, plug in a number over here into the first derivative to know if it's increasing, decreasing. Plug a number into the first derivative from here to know if it's increasing, decreasing, and plug a number in to the first derivative somewhere over here to know if it's increasing, decreasing. If you know where it's increasing and you know where it's decreasing, then you know where the relative maxes and relative mins are. But the second derivative test doesn't do that. The second derivative test has us plug these actual numbers into the second derivative. So I've got to take the derivative one more time to do that. Now, square root of 3 and negative square root of 3 is not the nicest thing to plug in, but since we only care if it's concave up or concave down, it's not too bad. If I plug this into the second derivative, I get negative something, which means it's concave down, which means that is a relative max or local max. And when I plug in square root of 3 into this, I get something positive, which means it's concave up, which means it's a local min because it's at the bottom. Good. You would figure out the same thing from the first derivative test. So sometimes you have an option. Now, here's how they're going to force you, and I'm sure we will pick at least one question like this on your next test, to force you to see if you know the second derivative test. What they would do is they would hide the function from you. They would hide the first derivative from you. They will tell you what the critical numbers are, so you don't even have to find them. And then they will give you the second derivative. If you know where the critical numbers are and what the second derivative is, the only way for you to figure out if those are maxes or mins is with the second derivative test. You can't use the first derivative if you don't know what the first derivative is. So that's how they force you to use this method sometimes. But again, if you practice doing the sign charts, again, just from a visual standpoint, hopefully you don't feel like you need to memorize anything from here. The only parts you really need to memorize, in my opinion, you probably already know, which is this. Second derivative is positive, concave up. Second derivative is negative, it's concave down. That has to be memorized. Okay. Any clarifying questions from the notes before we start to practice? Okay, then slide over to your circuit. Now, individually, I would say some of this is easier than some of the other stuff we've had to do this year. But what can be a challenge is just you've got to keep this stuff organized. It's not a ton of information, but you certainly can't get anything mixed up. You have to quickly be able to know if it's asking you where it's decreasing, you should be looking at first derivative. If you want to know if it's concave down, you should be thinking about second derivative. If you want a max value, well, that could be first derivative or second derivative test. Increasing, first derivative. Concave down, second derivative. Increasing and concave up, first derivative, second derivative. Local max could be first derivative test or second derivative test, whatever you feel like. Increasing, first derivative. Concave down, second derivative. Decreasing, first derivative. Inflection point, second derivative, and making sure it's a point, which would be the original function. Decreasing, first derivative. Decreasing, first derivative. Decreasing, first derivative. Concave down, second derivative. Concave up, second derivative. Minimum value, that would be first derivative test or second derivative test, whichever you prefer. Decreasing, first derivative. So it forces you to think about what each of these things are good for. The function has its purpose, the first derivative has a purpose, and the second derivative has a purpose. And you need to start organizing that information in your brain, when to use each one. So go ahead and start with number 1, please. And I'll give you a couple minutes to get started, and then I'll come around and help give some assistance. Of course, if I get a lot of the same question, then I will discuss it on the board.
What are you going to be for Halloween this year, Tyler?
What am I doing for Halloween? When is Halloween?
Like tomorrow?
Well, it's a Tuesday, so I'll probably come to school
Well, yeah. What, are you going to dress up as anything?
as a teacher.
Well, that's boring. Are you gonna go?
I'm gonna go trick or treating.
You could dress as like an 8-year-old kid. Just
I
like,
think the
give me
last
your
time I
first
went
picture.
trick or treating, I was like 12, and people were mad because I was too old to be getting out there getting candy. So.
Well, they're just grumpy. Okay. Be yourself. Yeah. Exactly. Or go to a party. I'm just saying, you should have some fun.
I have plenty of fun.
No, you don't.
I hate to tell you, but you know
Video
about
games don't
you know
cost
about 1% of my life. So.
Yeah, well, yeah.
One other thing to keep in mind is I have shown you all of the big things in this unit now. Extreme value theorem, mean value theorem, first derivative test, second derivative uses, second derivative test. So I'm sure there'll be a couple other small things, but most of the rest of this unit is just going to be a matter of practicing to get better at these questions quicker, less mistakes, and get all this information organized well in your head.
Does your wife not dress up as anything? Like, do you guys just sit at home?
What'd you get for an answer number 1?
7/2 to infinity. I did it in like 4 seconds.
Good. What'd you get on number 2?
Okay, well, I just finished number 1 because I was talking. The first like 20 seconds.
Okay, so,
Yes. Okay. What's your question?
Well, I got an answer and it's not
Okay. Then you must have a mistake.
For which one? You can do whichever one.
oh, you plug.
Just like something right there.
That's not the maximum value. That's when the maximum value occurs. The value would be the y value. That's like me asking you, like, how much is your paycheck? And you say Wednesday.
That's funny, actually.
So I got the answer, but my question is, like, if there's only one critical number, am I sure that this is where the maximum value is?
Critical numbers are the only place that the graph might be changing direction.
I took off last week.
So you're guaranteed that this is all below it. You're guaranteed that this is all below it. And if that's really the only critical number, that's the only place that it might have changed direction, so you feel safe saying that this still.
So there's not gonna be like this kind of thing going on?
No, because if this turned around, there would be another critical number. That's good. So when someone steals your phone, they'll know what number to give people. Just messing with you.
Christian messed with me without, like, the whole time. That's my mom's number.
What did I do?
Messes with my mom's number in my phone.
Actually, I didn't even think of that. Someone took your phone, if that was the number to your phone. Like,
Yeah, that's what he said.
Oh, yeah. Man, joke about that. So what's your, or I'm not saying that's you.
Bottom line, I'm like,
You're doing this would not be anything I ask for you. I don't know what these numbers are being plugged into, your line chart. Like, if that helps you, that's fine, but that's zero justification. I don't know what you're plugging that into, I don't know if you think those are positive or negative.
It's actually nice.
I've always been told that there's 4 trick questions.
Normally you go like south.
Others could be inverse, trig, sine, cosine graphs, law, sine, law, cosine graphs.
Like gone. I couldn't return
Those are the main ones.
And so,
Are you in, are you in,
I'm like, I had to go home now.
you probably run by Mr. Starkey.
And then I couldn't contact my parents.
Yeah, he'll probably like give you hours of package to his kids, just so you can tell.
So even when I got home,
If you want to see what one more.
I couldn't go nowhere.
What phone did you have?
Yeah, there we are. That's what I
Yeah, you can look at this one.
It's negative 18.
So for this is supposed to be the first one, right?
Maximum value, that would be at a relative max, which you could find from first derivative test or second derivative, whatever. That's your first derivative.
I literally
Oh, so negative 4. Negative.
Well,
I think you were in my best one.
you just like don't feel it.
First derivative test, test numbers around it in the first derivative.
In the
Second
derivative.
derivative test, you use the number. Doesn't matter, but what you're
So we plug these into the derivative.
first
But
derivative.
we're allowed to bring up, we're allowed to bring washes,
So negative 4, negative 4.
was white. Eraser off my paper, what's it?
That's
Smack
positive.
throwing it. I need to pick it up.
And then this one, negative 2. That's 4, right? Or negative 4.
If there's not an X on it.
So that's going down.
So is it, or you can plug X in it, but it's always
Max
gonna be
values
4.
occurred at
X equals negative 4.
is when, but the value is the y value at the.
Okay, so I plug negative 3 into the original. Okay, so 9, 18.
A lot of your justification, you're saying the right things, you need to start practicing it down. This one up, I can't assume you know why it's going up. You need to say, because I plugged this up into the first derivative and it's positive. This is going down because I plugged that number into the first derivative and it's negative. You don't show that, then you're not doing justification.
So does that work? If I put those?
It's greater than
It's the
0,
value,
less
so
than
you plug
0.
the X back into the equation.
Well, that means it's like,
Where's,
That's part you want.
if you're saying it's in the
I
first
just
derivative.
heard the face, that's all I did.
okay, so negative 18 plus 3.
That was the Wednesday thing I used to use.
Y'all are welcome to use a calculator for the arithmetic. Just don't graph the function and figure out if
That's
where
what
it's
the-
decreasing or increasing. You need to get the calculus practice. Arithmetic is fun.
I don't really understand how you, where, how you use the first and second, and why.
Then yesterday.
Well,
Then my calculator.
first derivative test and the second derivative test help you find relative maxes and relative
Next
mins.
thing.
Well, that is going to be a max value. This is going to be a min value.
What if you only have one number?
Then it's only changing directions once. So it's either like this or like this. So you've either got a max value or a min value. But you can still use first or second derivative test to know if it's max or min. If you want to know the value. The first derivative is good to know the slope, increasing, decreasing. Second derivative is good to know concavity, concave up, concave down. But if you need to points or values, you need to punch.
Take a day off. Oh, that's like nothing.
I think the first one that has a messier like derivative and such is like number 5 and number 6.
If you're turning 18 on your last birthday, you got it. Okay, no worries. If you want a new phone, I should.
So, I know this was designed, but the first thing I did was this, and would this be enough to tell me that there's no?
No.
But,
This, so it looks like you're trying the second derivative test. This is where the second derivative fails. Because if the second derivative is 0, you don't know if it's concave up or concave down. This is why you first derivative.
so I can just like this, like just find numbers around the critical numbers. And if I was concave down, that's just like the same as this, right?
Oh, cool.
Oh yeah. Like how do I even use
I have a bunch of them at home. I used to do like a key.
It's the same way you did on the other question. If you know where the critical number is, you can plug a number to the left of that into your first derivative.
I forgot that.
If it's positive, the graph's increasing. If it's negative, the graph's decreasing. Test the number to the right of the critical number to know if it's increasing or decreasing.
So I test it two different ways there because I tested the second one and it
Oh, wait, I'm sorry. You want to know if it's concave down. You don't care about the other stuff. Okay. Okay, so this is a, okay, forget everything I said. This is a critical number. It's also maybe an inflection point. So this is the only place that the concavity might be changing. So if you plug this in, do you think this was positive or negative?
should be negative.
This is negative. You should tell me it's negative and it needs to be concave down.
Wait. Actually, it should be positive.
You still need to tell me it's positive. Say greater than 0. Okay, and then to the right of the critical number, you can look at that. Okay, so that's why it's concave. Okay. So when is it concave down? I don't know, based on your work, it looks like
That's what screwed me on the concavity. Like, I wouldn't pay attention if it said like increasing or decreasing. And I was just like getting
If you want to know when it's concave down, you're testing numbers around possible inflections.
So I could do like
Okay, here's that one.
and that would, what is concave?
Wait, did you plug in oh, that's a 1/2 there?
Yeah.
You should have B or whatever, so I think 1/2.
One half is a critical number.
Oh, it is? Okay, so you're still mixing those up. Critical numbers are when it might be changing direction. You don't need that at all for concave down. You need to figure out where the possible inflection points are, which are these. When's the second derivative 0 undefined?
So 1/2. Yeah, 1/2 is a critical number.
I don't need to know anything about critical numbers in this question. I don't care when it's changing direction to relative to actual critical numbers. I don't need critical numbers.
So once there, it doesn't matter.
If it makes the second derivative 0 or undefined, it might be an inflection point. So you need to test around 0 and around 1/3. 1/3 on the other side.
Wait,
Let's do 0.
Okay, so what's it doing between 0 and 1/3?
Yeah, it should be concave up.
Because I don't know how we're supposed to, I don't know how whole thing's supposed to be. It's like,
Because I'm substituting like this interval into here, right? The second derivative. So it should be concave. Because all those values are like
Okay.
and then between 1/3 and 1, it also should be
Your work here, I think your stuff's fine, but you've got so much information on there that
Yeah,
it's
this
hard.
is really complicated.
You need to be more concise. Is it this one?
Yeah.
You need to list your maybe inflection points. You need to be testing numbers around that in the second derivative. And depending on if the second derivative is positive or negative or positive, then you can see what's concave up and concave down. You don't need anything else though. I don't know what that is. Is that a criticalness? You got to label what that is.
Should we do this one?
Then that would be a critical number two.
Stuff.
Shouldn't be getting zero. If it's making your first derivative 0, it's a critical number. You need to be testing numbers around it. Either it doesn't really need 0 or.
You messed up the word.
But I would suggest that you. Yeah, I wouldn't even try to do that. That would be a nightmare. So right here, see how you have two fractions? You could get a common denominator to squeeze those together into one big fraction. And then that big fraction would equal 0. The numerator equals 0, and the undefined one, the denominator equals 0. And that might be easier. You think it's concave up all the time? Yeah.
This was just a 2.
I'm not saying that's the answer, I don't know.
yeah.
Alright, anything else? I just assume that's fine and keep going. But then if you get another non-answer, then you need to start thinking about which one you're more interested in.
So I got none. So I got none there. And I think I'm not sure if this is the right way to take the derivative.
No, it's, you have to change, the real calculus way to do this is you change this to just piecewise function. Sometimes it does this, sometimes it does that. And then you can increase derivative each piece, but that's a nightmare and you don't have to do that. The cheese here is the graphics. You know what the natural log of X looks like in the graph? It's like there's log base P, log base 3, log base 10, not really like that. What does
would be nice.
what does the absolute value
That's like all I want.
There's always three conditions. So the stuff that was positive stays positive. And the stuff that was not becomes and then you can see
Wait, so what did you
graph is like you need to know what the base are.
thought you were supposed to plug these.
Oh, wait, you said.
Wait, so would this be derivative versus?
Zero, that's zero, obviously, because zero is when everything else above zero.
Concavity changes better places.
So just do everything zero.
Or in the fine. So you want to figure out what the second derivative
If it's,
is.
and every answer is zero,
Or
it's
fine.
Yeah.
So plus one.
Zero and 1/3.
What's negative? What's zero gonna be?
And you want to
You can go more negative than zero when zero, any negative is there. These are the ones that
Possible inflections. These are the only places the concavity might change.
Okay, so we do before that, so there's not.
Into what?
The second derivative.
The second, is it the second derivative is positive, you know, it's concave out, second derivative is concave. So you have around each of those, and then you can see where it's
Okay,
concave.
thank you. Oh, you're right, thank you.
Yeah, and that's where it gets tough, because these things all kind of sound similar, but then the slight difference between
Yeah.
critical
This is
numbers is where it
six.
might be direction. Inflection point is where it's changes. One uses first derivative, one uses second derivative.
Cool, thank you.
Guys doing okay? Y'all do the ACT last weekend? Nope. Oh, you're done? Happy with what you got?
Yeah.
What were you aiming for?
Just the
We got a
32.
What happens at 32?
Governors.
I knew you get some at 26, but
How'd you get this?
Governors and the fellowship.
Calm it down.
is that in-state only or? Yes. Well, technically plus or minus size, but imaginary numbers are not gonna show up on the graph, so you don't have to.
Into this.
So if we're talking about when the graph's increasing, decreasing, concave up, concave down, it's all stuff that you can.
Where the
Imagine-
Just
Just scratch.
Okay, but you just guess, yeah, but you just guess, I'm good.
Actually, you don't wanna have to measure the eyes and stuff.
So it's from.
Okay, if you're still working on 1 through 4 and you're stuck, please let me know so I can help.
My stomach right now is not my stomach, like.
Well, because it's absolutely not useful.
Any questions?
Critical numbers.
So we just have to.
And so you can increase.
We can just do the second.
I hate how like I always think I'm right. So whenever we're like doing problems here, and I'm always like,
So you're looking for.
Well,
Yeah, okay.
probably about 99 right now. There's a thing.
Yeah, we need to find second derivative.
Yeah, so you write down that. Basically, you get a bunch of units, first derivative, and watch these ones. Find it like, you want to figure out four.
Wait, I'm confused. That's not
He gives you each thing. Well, he
For
gives
second
you.
derivative, I got everything
Don't know about the rule.
Oh, damn.
So I we found very close to those inflection points. He's scrolling.
I think I had like a couple.
You're doing the right process.
So I put them in 1/6 between these two.
Also, it's not gonna be.
Did you get 1/6?
So if you're looking for a inflection point, if it's not 0 or under 5, there's no inflection point.
Inflection points occur when the second derivative is 0 or undefined and the concavity around it.
What is the second derivative?
Would it not be -1?
Like you set the second derivative equals 0?
Mhm. So it looks like if your second derivative is right there, 1/6 is the only number that might be an inflection point. So you should test numbers around it and test
You would get
concavity.
1/6 as the
This would be
inflection.
positive, concave up. You really need to say that because it's positive though.
Alright,
Less than
awesome. What about the
0, okay. So is x equals 1/6. Can I plug that into the function and get a number?
That's good.
Same thing. Okay, then it's the point on the graph. Is the concavity changing when x is 1/6? Then it's an inflection.
So what is this?
That's not f is 0, that's second derivative is 0, or second derivative is undefined.
And then over here.
That's how you
1/6
found this.
times that.
The candidates for inflection
That's the
points
same
come from
thing.
when the second derivative is 0 undefined. That's why you have this,
Yeah, don't
and
worry.
then you have to test the concavity around it. And once you know it's a point and the concavity is changing, now you can call it an inflection point.
If it wasn't 0 or undefined, then it's possible.
If the second derivative is never 0 or undefined, then there would be no concavity change. So,
Not for, that's for 1/6. What do you got?
What's an example?
I don't know, when the second derivative, what if the second derivative was 3? What if after you took the derivative twice, it's always the same thing?
That's when it's concave.
Well, if the second derivative is positive, you know the function is concave up. And so it would just be concave up all the time.
Basically, if you can't plug in your x value to essentially the concavity
We
never
plugged it
changes.
into the second derivative.
Okay. But here's the thing though. Let's say I want to know, I don't care what the function is. I want to know when is it concave up and concave down so I can answer questions. You don't want to test 0 and 1 and 2 and 3 and 4 and 1/2 and 1 point. You've got to have somewhere to start. So that's where the candidates, the possible inflection points come from. So you have to figure out where the second derivative is 0 or undefined, so that you can narrow it down to one number or two numbers, like 1/6. And then this is the only place it might be changing concavity. So then you only need to test numbers to the right and left. And if it's concave down here, it's always concave down. If it's concave up here, it's always concave up. Because this would be the only place the concavity might be changing. But you don't want to test everything. That's why you find those candidates or possible inflection points.
One square.
Okay, the way you're writing this counts out. But you're telling me this is your second derivative. On an FRQ, I'd have to go, that's still your first derivative. So you really should say first derivative is this, and then maybe an arrow.
I was thinking of it as in the absolute
Numerator and the non-zero.
no, you'd be surprised. I just typed it out.
This rule right here, when you take the derivative of this, all this looks fine. The quotient rules, this should be a minus. So that's a minus, which changes that. Your denominator is still correct. As I said, just even if you're on top, you get high. Imaginary numbers aren't showing up on the graph. So this shouldn't have to be.
Okay, what did you try?
That's a deep question.
That is. Like, did she work like that?
How do you know what's exactly?
Because it's -3 over 0.
Square root of 1. Okay, so you find the critical numbers, that's around there. Cross them by. What is that? Just imaginary numbers. Oh, yeah, I forgot. That's one percent. You can't, this isn't the true rule, this is absolute value sign. Where everything is a compound. Look at this. Ratchet. Like that.
If I multiply this by
So here's x squared.
if I multiply this by, it'd be just this.
You just want to get rid of that?
I'm thinking, oh my goodness. Like, when I'm saying something.
Minus 4, it's gonna shift it down 4.
If you like, just like.
Over that.
Oh, we should have it straight.
So I multiply by
When you subtract it from x, you subtract it from x squared. Okay, then that's down to 4.
I just fill it up water.
Yeah. Okay.
Just like,
I find the value.
So here's what it is.
check this out.
Make it always positive.
Then you can put the.
So part that was positive stays positive.
We'll find that out.
That was negative.
Multiply by 1/2.
So this is second derivative.
Yeah, second derivative. Inflection point, second derivative, minimum, max, cushion.
That is not right.
Thank you, Mr. Fowler.
You just left.
He quit. Wait, it's decreasing on the interval.
Yeah.
Then we go for
Decreasing. Yeah, there's two intervals. Thank you.
What did you do with the one like the square root? Because with the
Cross it off. Coming down. 0 to.
So that means it doesn't decrease,
Yeah, because that's
right? So it's none.
Look at this guy. Shut up. Okay, I helped you with some other.
It's on the front page.
Okay, that's what I got.
Yeah.
So decrease.
Okay.
Watch, on this one, you're gonna be so lost, and then be like, yeah, it's super easy.
Wait, say
No, we're stuck in 6. Did you do product girls?
Okay.
Find the X coordinate, so this is 1.5, so
Because this would be positive. And this would be what's
okay, so
No, this is not that bad when you, here, ignore the square root signs, every time you see a square root sign, it's right like this.
Did you solve this one? Because I got X equals 0, which is
What do you mean, whatever?
His house is yeah. Oh, just kidding. You get 11.
Should be negative 3.
We got, X equals 4.
Wait, maybe not.
Or maybe, there's got one or two, it's the interval, so maybe this is the critical number and this is the test. It's just the interval.
But it's concave down from 1 to 7.
It's true. What if it changes?
As long as you're considering it has concave, but not the point where it starts. When is the graph both decreasing and concave?
There has to be a way to solve it.
Oh, wait. If you put,
Okay, then I think something must be off.
put negative 3 in there, it makes it undefined. It makes it undefined.
Okay.
I don't know that though, without actually realizing what the answer was.
No, because he showed us.
No, I know that.
Was that number 7?
That was 7.
So,
Yeah, that's there's definitely times where
then
it's
you like especially on
decreasing.
another point per se. So there's concave down.
That makes sense.
There's times where it's both of us.
yeah, negative 3.
Do you have to do anything else besides this?
Took party last night. You're not gonna look at my dog? I'm on like number 6.
You've got 14 minutes of class.
Yeah, but like,
Because eventually, if it was one, you
You're the one not doing it.
Spent 30 minutes.
Even more.
yeah, you go.
We'll do like 3 problems like an hour.
Imaginary did show on graphs. All this stuff is about graphs.
Negative
Graph analysis.
So you have to take the first derivative, you have to set that equal to 0 to find the critical number, negative 4.
Oh, yeah.
exactly.
What's this today on the next chapter?
Well, he said that we're gonna take our quiz, then we're gonna start with next.
No, it's.
Well, that's it.
So we do this. So we're gonna start like.
Some of the ladies are you struggling with?
That's 3 times X minus 3.
Oh, so like we'll have like 2
We do some. He said, no, when I plug in it, pass it over to electric stuff. By the time. Oh, no, you got like 5. Isn't that a negative?
This is which is fine.
Oh, because that probably has
3 plus 1. 4 to 4. Yeah, they say they're oh, you plug it in. I was like, oh, there's gonna be 2 quizzes. Why? I realized I looked at 2 quizzes. Oh no, that's not why. Oh, I see. Why does it even seem that bad? It's like watching like all the time. I'm just gonna
We got the. I get the job. I have this. You can't say that. You're going to the product. So, well, part of it is you did. That level. No, for my so it doesn't matter. And power. It's not doing it. It's not doing it.
So for
Power.
this,
The one.
the answer is wrong.
I mean, I know this part right.
But this is the graph that I got. Or this is what I got. And then it's asking this question. Maybe I don't understand the question. But there's 3 points that I found. And this is concave action.
Oh, that's
And from negative infinity to negative 2. It would be
So we get, did you do this?
Oh, I just did what he did.
there's no
Well, I just everything.
Well, based on your picture here, it would look like it would be negative infinity to negative 2.
Well, it wouldn't just.
But that's like a possible function. So
Yeah, but it's still concave up from negative 3 to negative 2. So
oh,
that number should change. And then you also have this section, that's 2 to 3. It's concave up 2.
so it's not like 1 point, it's like an interval.
Yeah. It's concave up 2 and the amount of time.
Let me see if there's
That's fine, I'm just saying that's a lot of.
for this one, I got x equals 0 and I don't, it can't.
Whoa.
And this one, and I think one other, absolute value sign, it complicates it quite a bit. The only way to really do it by hand is to change your absolute value sign into a piecewise function, and then take the derivative of each piece individually. College Board doesn't make you do that for the AP exam, so they don't make you do that for the AP exam. So I do this with the graphical. You know, like natural logarithm.
This is already
Okay. Draw an x and y axis.
Solutions for 1, 2, 3, 4, 5, 6.
So just it's an x-intercept of 1.
First derivative should make
You need to slide it over just an inch.
It did say, it gave me a top line, it's just the bottom part of the function doesn't work.
X-intercept of 1.
It doesn't have it.
That's what all logarithms are.
This is just not very.
Log base E, log base 10, log base
I think that's how that works.
Now, to make this the absolute value of this, what is absolute value?
For 6 and 7?
No, just the absolute, what is absolute value do?
I'll mess up like
It has to be positive.
Okay, so stuff that's all
Yeah,
right,
like, I'll have to like spend hours on like questions and then test like
negative.
Especially in.
yeah, it's like
I go into a lot less than I should. When I sit there, like you're not supposed to do it that way, but you never see
it's definitely how it should apply.
Natural log of x. Just like that. Absolute value. Absolute value just makes everything positive. So stuff that was positive stays positive. Stuff that was negative becomes positive. But you can really only take that shortcut if you know what logarithm graphs look like and you are careful about what absolute value sign does. But then it's when x is 1.
So far,
Mr. Townsend, do you have Hot Wheels?
Christian.
It's while I'm walking
No,
to my
Christian.
desk.
No.
This is bias. Whatever that word is. What's that word?
Yeah, all you do
Tyranny. Guys, we could take them. You can. I'm kidding.
I'm like, yeah, but that's the thing. They're always been doing each other.
Oh, what here?
I'm glad you asked.
All right, guys, you're down to about 5 minutes, so you need to finish up what you're on, find a stopping place. For homework, I do need you to try the rest of these questions. All but number 9, 10, and 11 are worked out on the website. So I don't remember if those questions were easier or what. I don't remember why nobody ever asked those in past years, but...
Asked about which ones?
Huh?
Which ones did you say no one asked about?
I don't have videos on the website for number 9, 10, or 11. So typically that means people don't ask about it, which usually means it's easier, but...
No, I'm saying.
So, use those videos to help you finish up. Try the rest of those questions by Wednesday.
I don't know what the Even square root of -1. I got square root of -1. It's still the same.
I mean, you can also, since that numerator is so simple, I mean, it's really just a
One over what? Those just don't work. Minus what? Did you get both of your x's? What? Did you get it both of your x's for the derivatives?
if you want to write it like that, you can do
Let's see here. Okay, so not one.
But there's such an answer as none, just.
You're gonna get about the same answer.
Thank you.
So, is
Yes.
but since there's no.
It's not quite.
Whatever. It doesn't overlap. I think it's asking for where to vote.
Oh, and.
It's just not both.
You just have to test it. Oh, because the area where it's increasing. Okay. I'm still looking at it. And then the area is decreasing.
I'm on number 7. Tennessee. Tennessee? That's like 7 hours away.
Should I give up?
That's just preference. And my preference, you can clearly tell by the way. Huh? It just did.
You know me. I'll throw it from here. And I made it. I made it, Mr. Jones.
Wow. All right, I'm sorry I lied. Y'all still have 5 minutes. You still have 5 minutes. I looked at the wrong time.